Right, so welcome to the plane curves today. So we discussed elliptic curves last time. So these were cubic curves, smooth projective cubic curves over an algebraically closed field. So we had F, the so-called elliptic curve, which was a smooth projective cubic curve. And as always in our assumption, over an algebraically closed field. And the main thing was we saw that these elliptic curves are very interesting because they carry a group structure. Namely, we had seen that the set of points, so V of F, is a natural bijection to the degree 0 Picard group. So natural means after choosing a base point, but the group structure doesn't depend on the base point. So in that sense, it's natural, is a natural bijection to the degree 0 Picard group, Pic 0 and F. And that means that we can use that to give this set of points a group structure. Carries the natural group structure. And so that's very unique to these degree 3 curves. So this doesn't happen in any other degree of the curves. And we explored that to some extent. So there was the geometric construction of this group structure. And we had seen that it restricts actually also to arbitrary, not necessarily algebraically closed fields. If you do the whole theory first over the algebraic closure, say, and then restrict to a subfield, and that is compatible with that. And we saw how to apply that, for example, in cryptography, where this is actually used in nowadays cryptographic systems. So today I want to do also again talk about elliptic curves, but they occur actually in many fields of mathematics, so not just here in algebraic geometry and, for example, cryptography, so hence number theory as we saw last time, but also, and that's what we want to do today, in complex analysis. So there's also a way to approach these elliptic curves from an entirely complex analytic point of view, and that's what I want to just do today. That means today will be a complex analysis day. And we'll see pretty much the same thing again, namely that we can also consider elliptic curves or cubic curves from an analytic point of view. And there's like entirely different methods, but they will to do that, but they'll arrive at the same results. So the goal for today is over the complex numbers, hence. So we'll choose as our algebraically closed field the complex numbers. So you see similar results over C. So that would be the ground field from complex analysis. And so that's sort of like in lecture in between where we have a short break from algebra and do analysis. But again, we will see cubic curves also in today's lecture. So I mean, they just occur from an entirely different origin. So that's I think that's quite interesting, and I hope so that you have done some complex analysis. If not, I mean, the necessary stuff that we need here. I'll just write down everything we need from complex analysis. So it's not that much actually. Just ask these, so have you attended complex analysis? Oh, yeah, probably. So then you should be fine anyway. But otherwise, if not, so let's quickly recall what the setting is there. So first of all, just for the notation, so I guess in complex analysis, it's customary to have one complex variable, which is usually called z. So up to now, this was like the third coordinate in projective space. So here for today, we'll have z as a complex coordinate. In the complex plane. And therefore, we'll write x0, x1, x2 for the projective homogeneous coordinates of P2. So for the homogeneous. coordinates of P2 over C. So that will not be called X, Y, Z here today, because then we would get confused by that. So as I said, so first of all, so what do we need from complex analysis for that? So first of all, some very general introduction to that. So here's a quick introduction to complex analysis. And that would be as follows. So first of all, so the central concept of complex analysis is a holomorphic function, which just means a differentiable function. So if U in C is an open subset, then we would say a function f from U to C is called holomorphic if it's complex differentiable in the usual sense. So if it is differentiable at all points V0 and C, which means complex differentiable, and that means just that the usual definition applies, so that the derivative f prime of Z0, which would be defined as the limit of Z goes to Z0, so that's like a two-dimensional limit in the plane, f of Z minus f of Z0 over Z minus Z0, if that exists as a complex number at all points. So that would be a differentiable, just an ordinary differentiable, and that's called a holomorphic function. So here we'll need a slight generalization of that, namely of a so-called meromorphic function. And that is a function that is holomorphic at most points, but at isolated points it's allowed to have poles. And the pole would be a holomorphic function over some Z minus Z0 to some power. So we would say that f, again, from U now we have to go to, so at the pole we would assign the value infinity. So we say f from U to infinity is called meromorphic. If it is holomorphic except for some isolated singularities which are poles, so except for some isolated point S0, so isolated being there's a neighborhood that doesn't contain any other point. So for some isolated points D0 where f has a pole, i.e. we can write f of z is some f tilde z over z minus d0 to the n for some number, and then if so n would be greater than 0 then, so that we do have an actual pole, and so the value we assign there would be infinity. So that's why we need the additional point here. So with f of z0 formally assigned infinity. So that does mean, of course, that we can write, so maybe, yeah. Maybe put it in the numerator because then it looks better. So z minus z0 and f tilde z, and then n must be, or n could be a negative number, n less than or equal less than 0, because this n also applies to other functions, not just meromorphic, but also holomorphic functions. Namely, if we can write a function of that in that form, and the function f tilde has a non-zero value at this point, then this n would like be the order of vanishing of this thing. And that we would also call the multiplicity, and we can denote this by the same letter as we did it in the algebraic setting, and we call this mu z0 of f. So hence a meromorphic function. Can be locally written as so f of z is in that form, z0 to the n, and then f tilde of z with n is any integer, and so f tilde of z0 is actually non-zero, and that is if the function is not itself identically zero. So a meromorphic function not equal to zero can be locally written in that form, and then n can be considered to be the order of the zero or pole, and we would call this the multiplicity of f. So in this notation, the number we call this mu z0 of f, in the same way as we had it in the algebraic setting, is defined to be n and is called multiplicity of f at n at z0. And we would have, of course, the same interpretation and the same notion. So if n is positive in that sense, you would call it a zero. If n is negative, we would call it the pole of the corresponding order. If we do compare it already to the algebraic setting, of course, if we have a rational function in Z, that means like a quotient of polynomials, it will clearly be meromorphic on the whole plane. However, there's, of course, many more functions, right? I mean, there's more differentiable functions than polynomials, for example, like the exponential function. So the category in which we work here in the analytic setting is much larger than that of the polynomial and rational function picture that we have in algebra. Note any rational function in our algebraic sense, that means quotient of polynomials, is meromorphic but there are many more. For example, the exponential function. So it's really like a larger category to work with, but still we'll end up then finally with polynomials and go back to the algebraic setting, which I guess quite a nice feature of this whole picture of complex curves, so to say, not in the algebraic picture, but in the analytic picture. In fact, one could give a class not like plain algebraic curves, but also plain analytic curves over C, and that would have many very analogous statements with completely different methods, and that's just today now just a hint at how this would work. So let's just, as a remark, give some results from complex analysis that we need. So what are properties of holomorphic or meromorphic functions? The first one is, it's already hinted at this thing here, namely every holomorphic function can locally be written as a power series. One usually says it's analytic, and that means that every meromorphic function that has a factor or just an additional factor of z minus c0 to the n would be a power series with possibly negative exponents, which is usually called a Laurent series. So any holomorphic function around the point z0 is what's usually called analytic, i.e. locally a power series. Well, it means we could write f of z is the sum of k equals 0 to infinity, say it's bk z minus d0 to the k for some coefficient ck. And if we have a meromorphic function, so that means we have an additional factor of z minus d0 to some other power, then that means any meromorphic function has locally the form, well, exactly the same thing as here, just that you don't start with a 0 necessarily, but with the order, so there will be the smallest exponent occurring. So we start at n now, and we have the same ckz minus d0 to the k, and where n is before the order at the point z0 of that meromorphic function. And so that's usually called a Laurent series. It is just a power series with negative exponents, but the negative exponents are bounded here if we have poles. And so if you had some complex analysis class, you know there's another type of singularity which is called essential singularities, where you have infinitely many negative exponents, so they will not occur here. We always have only poles at this point. Yeah. So yeah, that's the one thing. So we can write it in this form. Then, very important, that is the one result of complex analysis is the residue theorem that we will need here. And that in one sort of simple form means the following, that if we have gamma, say, is a closed path in the plane, so in C, so something like that, that will be gamma that is positively oriented around some region of the plane. In region C, just as here, so let me not be too precise what this exactly means. So there would be concepts like winding number and so on, but we don't need this here. So it is just a curve that looks like this. And we have a function that is meromorphic on and in the interior of that gamma and actually has no poles on gamma itself. So, and f is meromorphic like in, so on gamma and in the interior of gamma, so in the region in between here. So without poles on gamma itself, then we have that if we compute the integral over this gamma of f of the dz, so we integrate that function along a path, and one can actually compute that without really computing any kind of integral, because the result is that you get some constant factor, which is 2 pi I, and then we sum over all points in the interior of gamma. Let me just write here z0, and then we have so-called residue z0 of f, which is written res z0 of f. And here the sum is over all points in the interior of gamma. And this residue is just in the expansion that we have here in this Laurent series, the coefficient at the exponent -1. So that is one of the nice features of complex analysis, that integrals can usually be computed without finding antiderivative functions. There's just a way to get that by having Laurent series or power series expansion and looking at coefficients. So with the sum over all z0 in the interior of gamma and the residue z0 of f is defined to be the c-1 coefficient, where this c means the thing here in the Laurent series expansion. So that is the second thing, and then there's one last thing, and that's then pretty much all we'll need today, namely C. Is that there is Liouville's theorem, and that's another one of these surprising complex analysis facts, which is that any holomorphic and bounded complex function, so any holomorphic bounded function that is defined on all of C. So here we allow no poles, so it must really be holomorphic. And it needs to be defined on the whole plane, not just in any open subset. It's actually constant. So that is pretty much a consequence of this power series expansion, and one proves this in complex analysis. So we just use that here today, and really don't want to prove that. That's not the goal of this class. So these are the things that I want to use from complex analysis. So it's pretty minimal, I guess. And that we want to now use to construct our elliptic curves from an analytic point of view. So what will we expect there? So we had seen already that an elliptic curve from a topological point of view is a torus. Now let's come to elliptic curves. So we know already that an elliptic curve over C is topologically a torus so it sort of looks like this. But that's just a topological picture, of course, not a complex or analytic picture of any kind. But we'll use that as a motivation to construct a torus analytically. And that's really already where it starts getting new compared to a standard complex analysis class. So we don't want to consider holomorphic or meromorphic functions actually on the plane or in open subsets of a plane, but on a torus. And the way to construct this is to consider a quotient group of the complex plane modulo a so-called lattice. So the first construction that we'll do, so that constructs a torus not just in a topological setting, but in an analytic setting. The construction that will be tori from lattices. And that would be the following. So a lattice is the following thing. So we take in the complex plane two vectors which are independent, linearly independent over the real numbers. So we choose, and I'll usually denote them omega 1 and omega 2 in the complex plane, and they should be linearly independent over R. And that lambda, so capital lambda is, I guess, the standard notation for that, be the subgroup generated by those two elements. So I could write it just with the usual generator brackets. And what I mean with that is just a set of all, say, m times omega 1 plus n times omega 2 with m and n integers. So a picture of that, of course, would be so maybe omega 1, I'll draw omega 1 so that it's on the real line. It doesn't have to, but it might be. And then omega 2 might be somewhere here. So that means these two vectors are linearly independent over R. And then they would generate a subgroup which looks like that in our picture. And of course it goes to both sides. And these points inside there, this group as a group, this is just isomorphic to Z2, of course, and that is called a lattice in C. Then lambda is isomorphic to Z squared with groups. And lambda is called a lattice in C. So for our constructions today, we will now always fix such a lattice. So lambda will be fixed from now on. For today, lambda will always be a fixed lattice. And what we want to do is we construct the quotient group C mod lambda, and of course that would then be at least topologically a torus, right? That's one way to construct a torus, by taking the real plane and then modding out Z squared. So R squared mod Z squared is one way to to construct a torus topologically. And of course, topologically, it wouldn't depend on which omega 1, omega 2 we take, as it's all, isomorphic as subgroups. But from an analytic point of view, it will make a difference. Note, if we consider the quotient group C mod lambda is then topologically a torus, and we'll often consider functions on that, and of course, well-defined function on this quotient on the torus would be the same as functions on C that are periodic with respect to lambda. So that means if you take any z and then add an element of lambda, you would get the same result. So it means functions of whatever type. So just set theoretic functions on C mod lambda are the same as functions, say as lambda periodic functions. So on C, where lambda periodic, of course, means that f of z plus omega is f of z for any z in C, and omega and lambda. And so that's just the usual well-defined thing. And we'll just use that interchangeably. So often we'll just write a function on C mod lambda, but write down a function on C that is then lambda periodic, which would be the same thing. In particular, if we talk about holomorphic or meromorphic functions, then the right-hand side here perfectly makes sense, right? So we could have a function on C that is meromorphic and lambda periodic, and we will consider that as a meromorphic function on a torus. So on such a torus, a holomorphic or meromorphic function is just defined as a lambda periodic function on the whole complex plane, so that it descends as a function to the torus. Yeah. 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 Exactly. So you'll find a representative modulo lambda of any point in such a parallelogram here. So any point is equivalent to one inside here. So you can in fact only consider that parallelogram if you want to. But here you also identify, say, this point with that point. So what? Oh yeah, you get the cylinder, exactly. So we have this, and then we identify the two yellow sides, which would give us a cylinder. And then we also identify the top with the bottom, and that will give us a torus. Okay? So that will make it a torus. And that's one way to construct a torus in topology. Usually you would then just take the unit square instead of any parallelogram, but topologically it doesn't matter. But as I said, analytically it does. So we'll see that today, and hence we'll use that general construction. And so this lambda will be given. So the omega 1, omega 2 are, of course, not uniquely defined. I mean, there's many choices to pick generators for that, but we'll need a lattice of that type. Yeah. So let's start with the first result that looks very familiar to us from the algebraic point of view. Namely, if we consider now a meromorphic function on such a torus, and consider its zeros and poles, and add that up, I claim that we will get zeros. So that means that we have equally many zeros as poles. And we have a statement already in algebra saying that if you have on a smooth projective curve, that any rational function has equally many zeros as poles. And the same is actually true here as well. But the proof is, of course, entirely different. I mean, as we're in a different category, and also as we've seen that there's many more meromorphic functions than just polynomials or rational functions. So it's in that sense, it looks like a stronger statement. So that's the first lemma. So any meromorphic function say non-zero, I should say, so not identically zero. Function f on C mod lambda, right? In the sense that it's a meromorphic function on C that has a that is lambda periodic. There's equally many zeros as poles counted with multiplicity. Namely, so that means in formulas, if you add over all points z0 in C mod lambda, and then add up the multiplicity mu z0 of f, then that will actually be 0, right? So the poles contribute with a negative value here, and these zeros with a positive, and they cancel exactly each other. That would be a statement that we had in the algebraic category as well. Then you don't have C mod lambda here, but a projective curve, but apart from that, it was exactly the same. So that also holds for meromorphic functions in the analytic setting. And as I said, so we clearly need a different proof for that. And yeah. One. The target space of the function. Well, if it's a meromorphic function, then at the poles it would take on values infinity. Yeah. So that's as I think, is it still on the board? I don't know. So I had said it here. So if a meromorphic function would have, I mean, either you say it's undefined at a pole, then you would say it's a singularity where it's not defined, or you just say assign it the value infinity formally. Yeah? So I could say f is, i.e. you could think of this as f C mod lambda to C union infinity. And infinity is exactly at the poles. Yeah? Yeah. Right. Yeah, so how do we prove that? So let's draw the picture of the lattice again. And here's our lattice. And what we want to do is we take such a, as we've already said, there will be a parallelogram like this that contains all the representatives of any point. And we take one, and we take one such that none of the zeros and poles, I mean, there will be only finitely many, as we have only isolated singularities, such that this path itself doesn't hit any poles or zeros. Right? So I won't draw just right here, but just anywhere inside here. So that's the standard parallelogram, just shifted by any way. Take here a parallelogram with sides, say omega 1, omega 2, so that each point has a representative inside there, and we have to identify the opposite edges in the same way as we did it here. Right? And what we want to do is we integrate over that path. So essentially we apply the residue theorem to that path, so that's gamma, to a particular function. And we compute the residue theorem. We want to compute the integral over this gamma, just around this parallelogram, of the following function. And you take the derivative of f over f itself, dz. So that integral here. So, well, I said already by the residue theorem, but actually also without the residue theorem, it should be clear what the result is, because the function f, as it's a function on C mod lambda, is periodic in lambda. So that means on this side, it looks exactly the same as on that side, and on this side, it looks exactly the same as on that side. And so the path gamma, of course, goes along this, so one's positively oriented around this, and that means that it runs along this path in that direction, along that path in this direction, the opposite direction. So that means whatever the integral is on this part of the path is cancelled by that contribution. And in the same way, this is cancelled by that. So even without any theorem, this is just 0 because the opposite side just cancel. But that will be clearly 0 as the opposite side will cancel. But we can also apply the residue theorem, and that would tell us that we get a sum over all points z0 in the interior, and each point in the interior contains one of the representatives exactly 1, so we can write it as C0 in C mod lambda, and then up to this factor of 2 pi I, we get the residue of f prime over f. Okay? So that would be the residue theorem. And so if you had a class in complex analysis already, like an introduction, you had probably seen this combination here of f prime over f as a function that counts the multiplicities or orders of functions. So the reason for that is if we write our f in the Laurent expansion, or not in the Laurent expansion, I write just z minus d0 to the n times f tilde to 0 of z, where n is the order and f tilde is non-zero. So this is mu z0 of f, and f tilde of z0 is non-zero. So that is like the way we can write a function locally around this point. Then we can actually compute what the derivative is and form the quotient and actually read off the residue directly and see that it is exactly the order of the function, so the multiplicity of the function. So I'll just continue the computation there. So from here, so if this is f, then f prime of z will be by the standard product rule of differentiation. This is n z minus z0 to the n minus 1 f tilde plus the first copy z minus z0 to the n, and then f tilde prime of z. And then we form the quotient of the two in the integrand. So that means f prime over f at z is, so we divide both terms by z minus z0 to the n f tilde. So here we have f tilde, but here to the n minus 1. So the first summand will be n over z minus d0. And the second will be, oh, z minus d0 cancels, and then we have an f tilde prime over f tilde. So that is just an expression for that particular function, f prime over f. And if you look at that, then you will see that the second part here is holomorphic at that point, because f tilde is non-zero at the point. You don't divide by 0 here. So that means this part is holomorphic. That means it doesn't contain any negative exponents of z minus z0, so the residue there will be 0. And here we exactly have an n times z minus z0 to the minus 1. So that means we can read off exactly the residue as this number here. That means the residue at the point z0 of f prime over f is just this number n from there. You can just read this off immediately from that form. And if we plug that in there, you see that, well, n is just the order at this point. We get the sum of the orders. And that we already saw was 0 because of the periodicity. So that is just the sum over c0 and c over lambda. And then 2 pi I times this multiplicity, mu z0 of f, and that means that the sum is 0. Right? So that's a way of showing that. So in the standard analysis, complex analysis class, we had this. It's a way to count zeros and poles in the interior of a region. And here we have the special case that we have this periodic parallelogram, so this torus, so that we know already the integral must be 0, and hence the number of zeros and poles must be the same inside. Yeah, so that is on a torus. We will have equally many zeros as poles. Let me just, so we'll continue with tori in a minute, but let me just digress for a minute to other curves. So if we had not just a torus, but a complex, one-dimensional compact manifold, I claim that there's a similar result to that, and that you would probably expect from algebra, because there we had seen like the statement that any rational function has equally many zeros and poles was true in any curve, not just an elliptic curve. Right? So what if we have not a torus, but a different analytic object, which is also a curve in that sense, and that would mean we have a one-dimensional complex analytic manifold, which we could draw topologically again in the same way as we did it before. It looks like a sphere with a couple of holes, but is also a complex manifold. So that's just a remark. I mean, we don't need this today, and we won't need it really in what follows. There will just be a couple of more remarks of similar type. So that's just an outlook, so to say, into something that's called differential forms, which is actually related to if you had a commutative algebra class, maybe you had considered differentials at some point, scalar differentials or something, or was this algebraic geometry? I don't know, maybe not. I don't know. So let me draw a picture. So I would draw like, it would look like this. For example, not just a torus with one hole, but something else. So say if, so let's give this another name. So say if X is a complex one-dimensional manifold. So that will be the corresponding object to our plane algebraic curves, but just in the analytic setting. Then I claim that there is a similar result to that one. There's a similar result to the lemma from above. And to state that, even one has to be a little careful, because this residue theorem here that we had, that we used, where we integrated over a function and then over dz. And if we have a manifold like that, then the problem, the first problem is that we don't really have a well-defined coordinate at every point, but there's actually different ways to choose coordinates at a point. In the plane, that's the clear thing. I mean, you have the one variable z, which is the coordinate on the complex plane. But if we have a manifold, that just means that locally around any point that looks locally like an open neighborhood of z, of the complex plane of C, but like the map between C, there's various choices, and so there's no well-defined coordinate. But the coordinate does occur here in the integral, right? You always write this dz at this thing, and a change of coordinate will change the integral. So the way around this is to consider so-called differential forms. Well, the problem is that there is no unique, a well-defined coordinate v such that something like a dz in the definition of the integral does not work. And instead, what one can integrate so-called differential forms. So differential forms are, so without giving a definition, are objects of a form f times dg. So in the same way as here we wrote f times dz, and instead of z you can take any function, so where f and g are functions. And so usually, let me call this, well, it's usually also called omega, which is maybe a bit, I just see now it's a bit bad because we called them omega as well. So anyway, probably change that, but maybe now call this omega. So there's no relation between this omega and that one. So this f of z dz would be a special case of that. But on general manifolds, it would look like that, and you could write this down without having a particular choice of coordinates. But then for such differential forms, there's a residue theorem again. Namely, which looks the same as before. So we have an integral over gamma and then some differential form, which is just omega, so that omega includes the d something. So there's no dz or anything behind that. And then we again have 2 pi I sum of the residues of this differential form, where z0 as before runs over all points in the interior of gamma. So it would be the same statement, just the objects that can be integrated, so in general, manifolds, curves, whatever here, the natural objects to be integrated over are not functions, but they would be differential forms of that type, of that kind. So as I said, it's just a remark. Don't do anything special with that. But the only thing we can see is then the argument from the lemma sort of carries over in the following setup. Namely, one advantage of such a compact manifold like that is that for a closed path on that, it's not well defined what the interior and what the exterior is. So if we have a path on that here, so let's see, I draw a path like that, so that's gamma. Then you would probably say, well, the interior is that here in the middle. But of course, you could also say the interior is the outside of the whole thing. Right? That works as well. That wouldn't work in the complex plane because that's unbounded. But there's some nice open manifold here in the middle and there as well. And that means there's a choice of which one, which part you consider the interior and the exterior. And that means that when you have a couple of poles and zeros here on that curve, so let me draw them as a couple of points. So here there are poles and zeros. And you take a gamma that is a small circle that doesn't contain any of these poles and zeros. Then you can first of all say, well, if the interior is that small circle here, I mean, there are no zeros and poles, and that means the integral that counts zeros and poles would be 0. But if you call this other part here the interior, then you get all the poles and zeros. And that would mean that, again, you get an equation like that the sum of over the zeros and poles is the same in the one interior or in the other interior. And as it's in the small one is 0, it would be 0 in the big one. Now, let's say that f be in the same way as before, a meromorphic function on x and gamma, a small loop not containing any zeros and poles. Then we can compute the integral gamma over. So now we need a differential form. I don't want to write f prime over f dz, but actually I would write d of the function f prime over f. So that is a differential in the above sense. And by the standard rules of differentiation, that would be, you could write it again as f prime. No, not that. That was not the wrong. You take d of log of f. That is, sorry. So you take the derivative of log f, and log f, the derivative is 1 over f times f prime. So that means that is the same as f prime over z, f prime of z over f of z dz. So it's just the same thing. So that tells you that the expression that we consider there is actually a differential. So there is a well-defined integration of that thing. And well, first of all, you get, as there are no zeros and poles, you would get 0. So now the reason is different. There's no periodicity. But now we get 0 since we have no zeros and poles inside gamma. Because as before, this integral will count you the zeros and poles inside by the residue theorem. But if you take the outside as the inside, so switching outside would be inside of gamma would give you that the same integral would be log f is now 2 pi I over the sum of all z0 and then the mu z0 of f. And so if we equate those two numbers, we again see that the number of zeros and poles, so counted with multiplicity, so total number is zeros. That means equally many zeros as poles. So it's just a different kind of argument, and but the same result. So that means the statement that we have equally many zeros as poles. So it's easier to see in the torus case, but it would hold on a one-dimensional complex manifold as well, as we would expect from the algebraic setting. Needs a different argument. In particular, one needs to pass to these differential forms. So that's one new concept there. And these differential forms are something that will occur again in a remark in the next chapter. So that's why I did it here. But for the moment, we don't need it in any way. And we just continue with our tori here and the result that we have equally many zeros and poles. Yeah. Yeah, so the point is that, so you know, for an integral, if you write an integral over a function, you always write f of z dz. So there's this dz. And I mean, the reason is just that you want to nag all the students that you have to write it, but it's actually important, right? Because what you do is, I mean, if you think of the definition of the integral, you multiply you add the areas of small parallelograms or something. You take a dz, a small z, and then times the value of f at that point, and you add this up. And that means if there is no naturally defined coordinate, so there is no naturally defined z on that thing, right? So on a manifold like that, you can pick a local coordinate, but it's your choice, right? So I could put a different one. And that means there is no well-defined z. And that's why I cannot write down f of z dz, or I mean, I can write it down when I have to say what the choice of z is. And that means that a function itself, so if I have a manifold and only a function on it, there's no well-defined way to integrate it. Right? That's the reason. So you need that z, and the differentials are a way around that. Right? So then you just say you have expressions of that form, so there's no coordinate inside there. But of course, you can rewrite dg in terms of a coordinate. So if you have a coordinate z, then you can write it as g primes. So the differentiation of g with respect to z times dz, and that you would use then for computations. Yeah. Well, anyway, so let's go back to tori, and so the main point to pass from now general analytic holomorphic meromorphic functions to algebraic functions and to cubic curves in the projective plane is a very particular meromorphic function, a very special one, and that we want to consider now. So the following, say, proposition and definition, namely that says that there is a particular meromorphic function that even has a special name, even has a special character in tech. Namely, it's the so-called Weierstrass P function. So again, a lattice is given, and the statement is there is a well-defined meromorphic function on C. So let's first do it on C, but it will turn out to be periodic later on. And the latter, so we'll write it by some curly letter P. So that's tech notation is \WP. And it is the following. So it's P of Z is defined to be 1 over Z squared plus, and then you sum over all lattice points, omega and lambda, without 0. And then you form the following expression: 1 over z minus omega squared minus 1 over omega squared. So the claim is that they well-defined meromorphic function, which means that, that the sum converges and that it's holomorphic except for some poles. And the claim is actually the poles are just, which are pretty much visible, are the lattice points themselves. So there's the 1 over z, that's the pole at 0, and that's the pole at all other points of the lattice. So it has poles of order 2 at all lattice points. and it's called the Weierstrass P function. So just the name is just the letter with a special P actually. And that would turn out to be a very important meromorphic function, as it is periodic, which is not quite visible yet, I think, because I mean it's almost, I mean every lattice point is treated in the same way here in the back, but the 0 point is special, so I guess we don't quite see that it's periodic, but it will turn out to be, and that means that P will actually be a meromorphic function on our torus, and that we will consider then later on. So let's just say something about the proof, or if everything today rather a sketch proof, but here it's really especially sketchy. So the main point is usually with these, as usual with these expressions, is whether the sum here actually converges, right? So it's a sum over a z squared, so it's like a double infinite sum. And of course, the question is whether the sum converges. Right? And let's have a look at this. Convergence of the sum. So for a fixed z, right? Which is not on the lattice. So let's look at the following. So let's regroup the points here. So that's really, as I say, it's really just a sketch. And let's have a look at an annulus in the plane around radius n. So that means here there's somewhere n. And we consider such an annulus from n minus 1/2 to n plus 1/2. And want to, first of all, sum all the values over all the lattice points inside this annulus, and then sum over n to get all the points in the complex plane. And that's just an approximation because we just want to check that the sum is finite, essentially, so that it converges. And so considering first points in an annulus like this, so of like width 1 from n minus 1/2 to n plus 1/2, then as an estimate, and you can make this precise, but I mean, it's just here, it's just an informal argument. The number of lattice points that you will find inside here is proportional to the area of the thing, because the lattice points are just equally distributed all over the plane, and the area of this thing grows linearly with n. So it's like the area itself is just like 2 pi and then n times 1, like the width. So that means the number of points of lattice points inside is proportional to n. So it doesn't mean like roughly n, but proportional to n. And so what does the function do there? So the thing that we sum over, so the 1 over z minus omega squared minus 1 over omega squared. So let's rewrite this. So and the summand, which is 1 over z minus omega squared minus 1 over omega squared. I'll just factor out the 1 over omega squared to get a 1 over 1 minus omega over z, I guess, squared minus 1. Let's just factor out the omega squared. And for large omega, so we want to check if the sum converges, so that means like the absolute value of omega is large. We just have the 1 over omega squared. And we can approximate that for, no, it's z over omega, not omega z. It's just standard fractions, yeah. So omega cancels omega, it's like that one, yeah. Otherwise, it would be pretty bad, because I want for large omega, this number here is small. And that means I can just have as an estimate, just replace it by the geometric series in the first term of that. So a 1 over 1 minus z over omega is roughly 1 plus z over omega. And that with a squared is roughly 1 plus 2z over omega. So that's just a geometric series. And then we have the minus 1 here, which cancels actually the 1. And so that means that is roughly in the order of 2z over omega cubed. And omega, like from the absolute value, is just roughly n, because we're in that annulus. So that means that is roughly 2z over n cubed. And so the point is that if we sum that over all n, hence the whole sum, is roughly the sum over n, so of the size of the annulus from 1 to infinity, and then the number of points is n, and for each point we get a contribution like that, so like 1 over n cubed, up to z, which is constant, doesn't depend on the sum. So that means the n is from here, the number of points inside the annulus, and each point gives a contribution of that type, and that's this. And that is the sum of 1 over n squared, and that's convergent, right? And so if you make this into an exact argument, you'll see that this sum actually converges. And you also see that for that to happen, it's actually important that we subtract this 1 over omega squared here in the back. Because I guess the first time you see a formula like that, you would probably be a bit surprised, because you subtract a constant here. I mean, that doesn't depend on z. So you subtract a constant in each summand. So you would rather think, I mean, why do you do that? I mean, everything that just shifts the function by a constant. Right? And why do you add a constant to each individual summand? But the reason for that is that without this, this wouldn't cancel, and this would go like 1 over omega squared. And then we had an n times 1 over n squared, which is 1 over n, and that diverges. So that means that thing here in the back, I mean, it doesn't change the function up to a constant, but the function, I mean, it wouldn't be well defined if we hadn't it there, because then the function, then the sum would not converge. So that's the only reason why it's there. And morally speaking, if it wasn't for convergence, I mean, you could essentially drop the thing here in the back, and then it looks very periodic, because you do the same over all points of the lattice, right? In fact, we'll see this in a minute. Right, so that means the sum converges, and the rest is then like standard theorems in complex analysis that if you have a convergent sum, that it's also holomorphic. So anything that's uniformly convergent of holomorphic functions will be holomorphic again. And I guess the poles we also see. So then, say by standard argument, which I don't want to make precise here, we can see that once it converges, it is actually meromorphic. And you see also what the poles are, or what's stated there, because the poles are actually visible from the function as it's there. So that is a very important function, as I say. And maybe let's first of all collect some properties of it. So as a remark, what are properties of this p function? why is just p function? So first of all, is it is what's called an even function. So that means if you take p of minus z, you get the same as p of z. And that's just because obviously the first term is invariant under z goes to minus z, and the lattice points are also invariant under z goes to minus z. And so that means you get exactly the same term here for the other omega. So that means p is an even function, which means p of minus z is p of z for all z. Actually, also we need the derivative of the function, and by standard rules, I mean complex analysis is always nice. We can compute that term by term. And what is nice, particularly for the derivative, is that all the constant terms in the back just drop out, of course. And so that means then for the derivative, you can take the sum over all lattice points and just differentiate the z minus omega squared. And that would hence be a sum over all omega in the lattice, so omega and lambda. And then we get the 1 over z minus omega squared. So this is a minus 2 over z minus omega cubed. And no, so that looks actually simpler than the original function because all the constant additional terms drop at the end. That is hence correspondingly an odd function, right? So it's the cubed here. So if I replace z by minus z, you get a minus. So that means p of minus z is minus p of z. And for the derivative, it is now obvious that it's periodic, right? Because the additional summons dropped out. So, and it is lambda periodic. That's visible from the form here. But that means now we can just pull this back to the statement that the p function itself is periodic as well. And one way to see that is, so let's draw again our lattice here, where we have p prime is periodic derivative, and pick any point omega, and consider omega plus a lattice point. So omega plus, no, z0, sorry, and then here we have the z0 plus omega. And we want to show that the p function is the same at those points. So let's, for that, again, integrate some function over some path, namely, we take here minus, I just draw a picture of that, so minus omega 1 half, and here plus omega 1 half. So I take the midpoints here of the lattice points. So that means that this, from that to that point, is the same as that. And then draw a parallelogram here. And in order to avoid this thing where we have a pole, I just quickly run around that. And this, and then I just connect those. That would be my gamma. And I integrate over that as before. And the function that I integrate is now not f prime over f, but just the derivative of the p function. Compute the integral over gamma, p prime of z, easy. Again, as before, we know exactly what the result is because we integrate over a derivative. And that means the result will be the function itself, so the p function at the starting point minus the end point, but they're the same, so the result is 0. So if we integrate a derivative of a function over a closed path, we always get 0. Right? Because that is, we'll get p at the end minus p at the start, but it's the same because it's a closed path. So we will get 0, and in the same way as before, the sides will cancel out because p prime is periodic, and so those two here will give the same contribution just with negative signs. Let me give this a different color. This here orange. So also, okay, these orange lines cancel out. And that means we only get the parts like from the bottom and from the top. But on the bottom, we'll get p of that point minus p of that point. Recall that we just integrate over the derivative of p. So it's p minus of the endpoint minus p of the starting point. And p is an even function, right? So that means that will be the same. So that will drop out as p is even. And from the top, we'll get p of that point minus p of that point. And because p is in because we integrate over the derivative of p. And so the result is that these points are the same. So that p of z0 plus omega is p of z0. So actually, as one might expect already, as the thing where it maybe doesn't look periodic is just a constant that doesn't depend on z. That's actually true in the sense, so this is a periodic function. And that means that it actually descends to a function on C mod lambda. And it will be a meromorphic function on our torus. That's the main property that we need here. Write this down, so P is well defined on C mod lambda. So we consider the meromorphic function on our torus. And now so that's the main function that we want to consider, and it has one main property. And that's the proposition here that this P function satisfies a differential equation. For P. Namely, the statement is that I won't write it down explicitly, but just say there are constants. Namely, 4 of them, C0, C1, C2, C3, complex constants, such that for all Z and C, we have the following differential equation, namely the derivative of P squared is a polynomial in P, a cubic polynomial, the first time where cubics appear, with these coefficients. So namely, it will be C3, PZ cubed plus C2 PZ squared plus C1 PZ plus C0. Okay. That is the statement. So it means the P function satisfies this differential equation. Derivative squared is that cubic polynomial in P. And in fact, one can make these constants explicit. So if one follows the proof that we'll do in a minute, through, then one could say what these constants are, we just don't care. So that's why I don't write them down. So let me put this in brackets. In fact, one can show by direct computation that the numbers are as follows. I think C3 was 4. So C2 is 0, and now it gets weird. C1 was minus 60, and then the sum over 1 over, I have to look this up, 1 over omega to the sum power, which is 4. 1 over omega 4. The omega runs over the lattice without 0, and C0 is minus 140 times the sum over all omega and lambda without 0. 1 over omega to the 6. So as I said, it really doesn't matter for us. We just say one could compute those numbers, and of course they do depend on the lattice. So if you pick a different lattice to start with, you'll get a different equation, but it's always a cubic equation. So it's like a quadratic differential equation in the sense that the derivative occurs with a squared, it's not a linear one. And it equals a cubic polynomial in P. And that we'll use then to make this into an elliptic curve. So the funny thing is that using complex analysis, the methods in complex analysis are so strong that one can actually prove this differential equation without actually computing that this is true. You would say, it's a concretely defined function, so you could, in principle, just compute both sides and just see that they agree. But of course, that's not overly nice because you have, after all, a double sum over a lattice, and then you cube that thing or take derivatives, so it's not that nice. But there is an easy way to see that such a statement holds without making these actual computations. And that is the following. So let's have a look at the left-hand side first. So the P prime, we had seen that, I haven't written it down there, but we had seen it's an odd function. And it has poles in the lattice points of order 3 now. Right? So that means because here we have 1 over z minus omega cubed. There we have poles of order 3 at all lattice points. So that means the left-hand side will, in the origin, which is a lattice point, will have a pole of order 6. And it's an even function, right? Because it's a square. And P is even. And P prime is odd, but it's the square of that. So namely, we know that P prime of z is an even function and has a pole of order 6 at 0. And that means if we make a Laurent expansion at 0, that would look as follows. So we have a P prime of z squared would be some, so that we call these coefficients, was it like C3 already? Yes, so. Oh, maybe it's not yet. So these are different numbers, right? It's not the C's yet. Yeah. So they would try. Or we call them A something. So we'll have an A minus 6 z to the minus 6 plus A minus 4 z minus 4 plus A minus 2 z minus 2 plus A0, and then plus higher order terms. Order in Z. So it's a pole of order 6 and it's even, so it contains z minus 6, minus 4, minus 2, 0, and then higher order. On the right-hand side, we have that the P function is an even function and it has a pole of order 2. So that means that P of z has a pole of order 2, that has a pole of order 4, that has a pole of order 6. On the right-hand side, so P of z has a pole in 0 of order 2 and is even. And so that means the terms that we have in there, so P of z cubed has terms z to the minus 6, z to the minus 4, z to the minus 2, z to the 0, and then higher order. And similarly the others, right? So squared has terms z minus 4, z minus 2, z0, pz has z to the minus 2, z0. And of course the constant at the end, which is 1, just has a term z to the 0, and then nothing anymore, just z to the 0, right? So these are the 4 terms that we have there. And that means that at least there are coefficients C3, T2, C1, C0 by solving this linear combination of this linear equation, such that when you subtract those sides, so this minus that the z to the minus 6, minus 4, minus 2, and 0 cancel. That's just linear algebra. So linear algebra. We have four parameters to pick and 4 conditions. They need to make these 1, 0. Linear algebra. We can find now C0, C1, C2, C3, such that if I take the difference of the two, so P prime of D squared minus C3, P cubed minus and so on minus C0 has no terms anymore, Z to the minus 6, minus 4, minus 2, 0, but only has positive exponents of Z. At 0. But what does that mean? That means that this function, let me call this f of z, is at 0 holomorphic, doesn't have impulse anymore, and has a 0 value, right? Because it starts really with positive exponents. But it means f is holomorphic around 0 with value 0. But it's also periodic, right? It's lambda periodic because it's made up of the p function and its derivative. So it's also periodic. And by the way, it's not just holomorphic. So that means if we look at, if it's periodic, that means it takes on all value in this one parallelogram at the that takes all representatives. And if it's holomorphic then around 0 and it's periodic, then it means it's also holomorphic around all the lattice points, because it's periodic. And of course, then it's holomorphic everywhere, right? Because, I mean, the only points where the p function is not holomorphic are the lattice points. So that means f is holomorphic around all lattice points. But then also f is holomorphic everywhere. Since p and p prime are holomorphic at these other points. So it's a holomorphic function on all of C. And it's periodic, and that means it takes on all the values on the standard parallelogram, which is compact, right? And that means it's a bounded function. Moreover, f takes on all values, all its values. On one parallelogram already. On one of these parallelograms of periodicity, and which is compact. And that means that f is bounded. And if it's bounded and holomorphic, then it's by Liouville constant. And we had already seen that f of 0 is 0. And here. And that means f is identically 0. So that means we could actually check the whole differential equation by just adjusting 4 parameters. And the rest just follows from general theory. I mean, that's really very nice. And these are often things that happen in complex analysis. I mean, these statements like, for example, Liouville's theorem or the residue theorem, I mean, they are so strong that often, I mean, it is sort of, I always say, I mean, it is called analysis, but oftentimes you don't really do analysis because it's, I mean, everything boils down to a couple of coefficients that one could quite easily compute. To know what's the point about this differential equation, I mean, you obviously here see a cubic equation, and that will make this into a cubic and hence into an elliptic curve. So the corollary from that is that there is a bijection. So in the same way as we had a bijection in the entirely algebraic setting between the set of points of a cubic curve and the degree 0 Picard group, here we get a bijection between an elliptic curve and this points of a torus. Namely, so call this maybe psi, from the torus C mod lambda to the points of a cubic, where the cubic is essentially given by this equation. So with f, then we wanted to call the coordinates x0, x1, x2. So it is x2 squared. I want to write down x2 squared minus x3, x1 cubed, minus c2, x1 squared, minus c1, x1, minus c0, and then we have to make this homogeneous. Right? So that means here we need an x0, here we need an x0, x0 squared, and here we need an x0 cubed. And the map is just sending a point to, in the x0 coordinate 1, in the x1 coordinate p of z, and in the x2 coordinate p prime of z. So essentially we just see there is a cubic equation between p and p prime, and that will give us a map from the torus that's well defined now in the torus because they're a periodic function to v of f. And actually that it goes to v of f is exactly this equation. So I guess we see that. So it will be, it will be well defined because they are periodic, and it will map into v of f. That is just the differential equation. A note. It's obvious by the above properties. That this is well defined. So that means p and p prime are well defined on C mod lambda. And goes, so has its image in v of f. That is just the differential equation. So the bijectivity is not obvious, I agree, but one can check this. I mean, as the time is up, I would probably skip that, but it's in the proof, it's in the notes. So in the notes, because I want to start with a new chapter next time then. So this is a bijection. You can also use the arguments before to do that. And that would give a group structure on V of f. And again, because C modulo lambda is obviously a group. And let me just remark is, so this again gives V of f a group structure. Namely that of C mod lambda. And one can check that, I put it as an exercise, I don't know if we do that on the current sheet, we'll see, that this, I guess we haven't planned it yet, but you can check that this is the same group structure as before. It's just a different way to do the same group structure. And check. So this agrees with the group structure from the Picard group, from prig 0 of f. But what we clearly have is that the structure of the group, what kind of group is easier to see in the complex analytic picture, right? Because C mod lambda is just a torus. We see a picture of that thing. And also what the group structure is. So for example, if you want to look at like points of order something, the group structure of C mod d squared is quite simple, right? Whereas the group structure of the Picard group would not be clear at all. So in the sense of how many points of order, whatever do you have or something, that's hard to see in the Picard group, but it's very easy to see here. So in that sense, the analytic picture, for example, would be nicer, but it gives the same result. And yeah, so that's what I wanted to do actually for that thing. Just as I say, it was just an excursion to analysis, and if in case you're interested in these kinds, so every now and then there's also classes here on complex analysis curves. So they're usually called Riemann surfaces. So we probably heard that as a class that's taught every now and then. And so Riemann surface is pretty much the complex analytic side of plane algebraic curves, and they would do things like that. So you can do everything essentially we do here in class algebraically. You can also do analytically, and it's just one short glimpse at how this might work. What? It is going on now, like the Riemann surfaces. Yeah. Great. Okay. So that is, yeah, I wasn't aware of that, but so I don't know if they do that, but I mean, they do just curves from this analytic point of view. All right, so are there any questions? Well, then I'll stop here, and then next time we can go back to algebra actually and have one last chapter on where we do more with devices and have a theorem to end the lecture with. All right, so then let's stop here for today.